Welcome to The Explainer. Today, we're taking a seriously fascinating journey straight into the very heart of embedded systems. We are going to decode the architecture and assembly language of the PIC16F84A microcontroller. If you've ever found yourself wondering exactly how software commands physical hardware at the absolute microscopic level, well, you're in the right place. We won't be relying on any high-level, abstracted programming languages today. Instead, we're stripping away all those layers to work directly with the silicon, manipulating bits, managing memory, and controlling power with absolute precision. So grab your coffee and get ready because we are getting right down to the bare metal.
Okay, let's dive into this. Today, we're breaking things down systematically into 5 parts: setting the PIC foundation, power, timers, and prescalers, mastering the interrupt system, coding the alarm interrupt, and we'll wrap it all up with bit rotations and comparisons.
Section 1. Setting the PIC foundation. You know, every robust structure needs a solid bedrock, right? And in the world of microcontrollers, that bedrock is the very first line of code your chip reads when it powers on. This happens at what we call the reset vector, specifically at memory address hex 00. But before we write functional code, we actually have to talk to the assembler itself, using things called directives. Think of directives as instructions for the software building your code, rather than instructions for the chip. The list directive, for example, is absolutely crucial. It explicitly tells the assembler to turn the listing option on and generate the actual hex file, the literal machine code that's going to be flashed onto the PIC's program memory. Right alongside that is the include directive. Instead of rewriting standard definitions for every single new project, include elegantly imports a pre-written header file directly into our environment. This prevents frustrating typos and ensures a perfectly consistent code compilation every single time. Now, what's really interesting about this header file mapping is how it handles special function registers, or SFRs. Inside the PIC, these SFRs control literally everything, from memory banking to hardware ports, but natively, they live at raw hexadecimal memory addresses. Without this header file, every time you wanted to check the processor's status, you'd have to remember to query memory address hex 0003. By including the p16f84a.inc file, those raw addresses are mapped to human-readable names. You can just type status, port A, or intcon. It beautifully bridges the gap between our human logic and the silicon's memory mapping.
Moving on to Section 2, power, timers, and prescalers.
Embedded systems are frequently deployed out in the field, totally isolated, and running solely on portable battery power. And let's be honest, a microcontroller that wastes power is basically a useless microcontroller. To conserve that precious battery life, the PIC16F84A utilizes a brilliant feature called sleep mode. Executing a sleep instruction places the processor in a state of suspended animation. The internal clock stops, code execution halts, and power consumption drops to near zero. It just waits there patiently for a wake-up signal. But what happens if the program freezes before it can sleep or gets stuck in an infinite loop? Enter the watchdog timer, or WDT. This is a completely independent timer running on its own internal RC oscillator. If your main program stops responding and fails to clear the watchdog timer for approximately 18 milliseconds, the watchdog assumes the system has crashed and forcefully resets the entire processor. It's your ultimate automated failsafe. Now, when the chip is awake, it needs to keep track of events, which brings us to the Timer Zero module, or TMR0. This module has a bit of a split personality. You dictate its behavior using a single bit in the option register called T0CS. If you clear the T0CS bit to 0, you enter timer mode. In this mode, the module counts along with the chip's internal instruction cycle clock. It's literally tracking internal time. But if you set the T0CS bit to 1, you flip it into counter mode. Now the module completely ignores the internal clock and instead looks outward, incrementing its count every time a high or low pulse hits an external physical pin, specifically pin RA4. So it shifts from tracking internal time to tracking external physical events. Pretty cool, right? Sometimes, though, events happen way too fast for an 8-bit register to count effectively. That's exactly why the PIC gives us a prescaler. Think of it as a programmable gear reduction system for your counts. By looking at the prescaler rate select bits, PS2, PS1, and PS0, you can actually configure the prescale ratio. You can slow down the counts by a ratio of 1 to 2, all the way down to a massive 1 to 256. But there is a catch here. There's only one prescaler circuit on the entire chip. The PSA bit in the option register acts as a sort of switch track. If you clear the PSA bit, the prescaler slows down timer 0. but if you set it, it gets reassigned to extend the timeout period of the watchdog timer. You basically have to choose which module needs it more.
All right, Section 3, Mastering the Interrupt System. If you want your microcontroller to interact seamlessly with the real world, it needs to be able to react instantly. Interrupts are essentially the microcontroller's high-speed reflex system, and the command center for this reflex system is the INT-CON register. Looking at this register breakdown, you can see bits acting as both switches and indicators. We actually have 4 distinct sources that can trigger an interrupt: an external pulse on the RB0 pin, a timer 0 overflow, a state change on port B, or the completion of a data write to EEPROM memory. For each of these sources, INT-CON has an enable bit to arm the trap and a flag bit that physically flips to 1 when the event actually occurs. And this brilliantly illustrates how the internal hardware logic of the interrupt system is structured. Each specific flag and enable bit feeds into an AND gate. This means only if an interrupt is enabled and its flag is triggered does the signal move forward. All of those signals then funnel into a massive OR gate. But look closely at the final logic gate on the right. None of those signals can reach the processor unless the GIE, the Global Interrupt Enable bit, is set. GIE is the ultimate master switch. If GIE is 0, the processor just ignores all interrupts, no matter what crazy stuff is happening outside.
Moving to Section 4, Coding the Alarm Interrupt.
Let's take all this architectural theory and translate it into some practical assembly code. We're going to design a simple security system that trips an alarm when a door opens, which triggers a rising edge on our external interrupt pin, RB0. The exact millisecond that door opens and the RB0 pin goes high, the processor physically halts its main program and automatically executes a very rigid 4-step sequence. First, it pushes its current location onto the stack so it remembers exactly where it was. Second, it instantly jumps its program counter to a dedicated memory address, the interrupt vector at hex 0x4. Third, it executes whatever service routine code you've written at that address. And fourth, it clears the hardware flag and returns to its original task. So, what does that code at address hex 4 actually look like? Well, here are the first 2 lines of our interrupt service routine. The very first thing we do is BCF intcon intITF. That stands for bit clear F. We absolutely must manually clear the INTF flag bit back to 0. If we don't, the chip will think the interrupt is still happening and it's going to get trapped in an endless loop. Once the flag is cleared, we use BSF port B6, bit set F, to send a high voltage signal out of pin 6 on port B. This physically turns on our alarm siren or flashing light. Okay, so now the alarm is blaring. We want it to stay blaring until a user physically presses a reset button wired to pin 3 on port A. We handle this with a polling loop. The real genius here is the instruction BTFSS, bit test F skip if set. The chip checks the button on port A bit 3. If the button is not pressed, the bit is 0, so it does not skip and simply executes the go-to read instruction, looping back infinitely. But the millisecond the user presses that button, the bit becomes 1. The processor skips the goto command, breaks out of the loop, and moves forward. Having escaped the loop, the crisis is officially averted. We execute BCF port B, 6 to clear the pin and silence the alarm siren. Then comes a truly critical command, RET-IFE, which stands for Return from Interrupt. This instruction pops the original saved address off the stack, sends the processor exactly back to the main program loop where it was originally interrupted, and automatically re-enables the global interrupt enable bit, so the entire system is armed and ready for the next event. Finally, Section 5, Bit Rotations and Comparisons. Let's move on and see how this all builds together. We've controlled hardware ports and timed events, but how does the PIC evaluate raw values in assembly when we don't have the luxury of high-level math operators? Let's look at how microcontrollers build the foundational skill of bit rotation. Microcontrollers frequently need to communicate serially, sending data one single bit at a time down a single wire. Assembly provides RLF for rotate left and RRF for rotate right. Notice how when you execute an RF, the entire 8-bit value physically shifts to the right. But the bit that falls off the end doesn't just disappear, it gets pushed directly into the carry bit of the status register. By continually rotating and checking that carry bit, you can stream an entire byte of data out to another device. So the crucial point is how we handle logical comparisons. In languages like C, checking if X is greater than Y is literally one line of code. In assembly, we have to be a bit more clever. We do this by actually subtracting the values using the sub-LW command. Once subtracted, we check the microscopic fallout in the status register. We use BTFSS to check the carry bit, which is bit 0.
If the subtraction resulted in a negative number, the carry bit drops to 0, meaning our first number was less than our second. If it's 1, the result was positive, so we then check the 0 bit, which is bit 2. If the 0 bit is 1, the result of the subtraction was exactly 0, meaning the two numbers are perfectly equal. It's amazing. We are literally building complex logic out of the most basic arithmetic.
And there you have it. We've gone from setting up a simple reset vector to managing power, manipulating hardware interrupts, and performing complex math bit by bit. You aren't just writing code anymore. You are choreographing the microscopic electrical signals inside the silicon itself. You now have the blueprint to command hardware at the lowest, most fundamental level possible. The only question left is, what complex bare metal systems will you build next with these foundational skills? Keep experimenting, keep learning, and I'll catch you in the next explainer.